Hello, everybody, and welcome to the end of day 5. We hope you guys have been having fun out there building, designing those habitats. We've seen some submissions come in already for your daily reflection. Cannot wait to see the other creations, and don't forget to submit those because tomorrow, Christy and I will be back giving away some more swag. Christy, how are you feeling today?
I'm feeling great. Excited to hear about how everyone's day has gone.
Yeah, I'm still I'm laughing still about that kangaroo racing that Australian students
I'm pretty
started.
gullible.
They were just making up stuff at that point. They're like, we're gonna get these American hosts.
I know.
Well, tell us in the comments how you guys are doing. And we're just excited to go ahead and bring on this. I don't want to say, I keep wanting to say evening, but it might be the morning for you, the middle of the night for you, whenever you watch this. But we have a really awesome and exciting presentation. So before I bring him on, our speaker is Mr. Chris Kennedy. He's a space architect. He's been one for 30 years at NASA Johnson Space Center and is recognized as an exploration habitat expert. Prior to designing space systems at NASA, Mr. Kennedy worked with numerous architectural firms around the United States. Currently, Mr. Kennedy is the founder and president of an architecture and space architecture firm and an adjunct assistant professor of space architecture at the University of Houston Sasakawa International Center for Space Architecture. His vision is to provide habitation capabilities to enable lunar and Martian ecosystems to thrive in support of human exploration and resource consumption, to become Earth independent while establishing a permanent, sustainable human presence on the moon and Mars. So if you can't tell, he has a wealth of knowledge, a lot of insight for all the students out there who are designing their habitats for this mission. So let me go ahead and bring him on. Welcome.
Hello, everyone.
Hello.
So where are you joining us from?
Just north of Houston, where I live. So Houston area, basically. And I am thrilled to be here. Do you have any more questions before I get started?
No, we'll go ahead and share your slides, and you're welcome to start when you're ready.
Okay, great. Thank you. So I just wanted to just say how honored I am to be included in the Space Team's International Mission Oz design team effort. And today I'll give you a brief overview about space architecture and designing exploration habitats. I feel that space architects have the responsibility of bridging terrestrial architecture with space architecture. So my goals of the lecture today are to inspire you, the next generation of space architects, engineers, thinkers, and dreamers, to share my 36 years of knowledge in space architecture and habitat design, and introduce you to habitat design and their considerations, providing you with enough data and information so that you can continue the great work that you're doing. Let's see. There we go. So I did work 30 years as an architect or a space architect at NASA, Johnson Space Center, and I got to meet a lot of very smart people, including Greg, and many of those people are much smarter than I am. And most notably, I got to work with Buzz Aldrin numerous times. I've worked on many design projects and published many papers and chapters and books and so on over the years. And I did have the fortunate to work on a couple of projects that we were able to patent. And one of them actually won NASA or the Government Invention of the Year in 2017. I'm also a licensed architect. So my career started as an architect, or actually a designer, draftsperson, excuse me. And it led to the interest in pursuing greater architectural feats. And somehow I ended up at University of Houston. And from there, as they say, is history. I ended up working at NASA for 30 years. So space architecture, what is that? It's really, excuse me, the theory and practice of designing and building inhabited environments in outer space. In other words, the design of living and working environments, the internal architecture of space facilities, habitats, surface outposts, bases, and vehicles. Anything that you're putting humans into or interacting with humans. So an exploration habitation is that recreation of Earth's environment for the purposes of sustaining human life. It's very important because habitats are those pressurized human-rated volumes that provide a safe and healthy environment for humans to work and live in. And when I say safe and healthy, when I say healthy, it's both physically or physiology or physiologically and psychologically, the mental health as well. So let's talk a little bit about humans surviving versus thriving in space. The Apollo era and even now to International Space Station is really about understanding humans surviving in space. Very engineering focused, engineering led, minimal functionality, minimal capability and technologies, and minimal human accommodations for the most part. As we see this tipping point or transition to commercialization of space and much more activity going on, we're seeing the second generation of space stations, which are really looking at how can humans thrive in space? How can we develop capabilities on the moon, Mars, or in low Earth orbit or Lagrange points so that the humans can thrive in space and not just about surviving there, although obviously survival and safety is key part of that. And so architects are helping to lead the way in the way of space architecture, human-centered design, and human systems integration. So let's talk a little bit about sustainability, because I know that there's a big emphasis with your class and the work that you're doing here. So sustainability means a lot of things to a lot of people, and so space sustainability maybe, some people think of it as ensuring that all humanity can continue to cover or to use outer space for peaceful purposes and social economic benefits now and in the long term. By default, space missions must be sustainable as possible because suppliers are limited on the spacecraft. You have to take all your consumables and all your supplies and spares with you, or you have to figure out how to manufacture them there. So a moon base that does not rely on regular supply missions is more viable and could last indefinitely if it is created with its own fuel from local resources. So, to sustainability can mean a number of things, and I highlighted a few here. One of the key aspects, I think, to sustainability is recycle, reuse, and repurpose. Everything we take to space or take on our journey or to the destination, to the moon, Mars, or another planet, we need to think about how that can be used. So if you have a descent lander and then you offload your cargo, well, could you reuse those tanks? Could you break apart that lander and reuse it to create new structures or other ways? We need to think about, from a sustainability standpoint, reclaiming all the water and waste to the extent possible. We need to think about water production and oxygen production and food as well. And then, of course, you have to get rid of the CO2, the carbon dioxide. So there are a lot of environmental considerations in sustainability. We need to think about your resources and how you might utilize them. And robotics are going to play a large part in aspects of sustainability because they are going to be working side by side, or in some cases, precursor to the humans doing the exploration or settlements. And then some of the new capabilities and technologies in 3D printing and 3D manufacturing, servicing and repair. And there's some examples and pictures here on the right that kind of show you examples of some of those types of capabilities. In situ resource utilization is really important to, I think, to aspects of sustainability, because you need to approach it from living off the land, making use of what is already there. So during early humanity, explorers had to live off the land. So clans, tribes, and communities banded together to survive in numbers. They would find, gather, or grow food. They would find fresh water and cultivate that water. And then they would build shelters for protection from the environment and predators. So if you think about it, Space exploration and the things that we want to do is really kind of taking a page of what we've been doing our whole existence as humans, is living off the land. And so other aspects of living off the land, especially for off-world and not here on Earth, other places like the Moon and Mars, is power generation. You need to be able to harvest power from the sun or make your own power from nuclear powered capabilities. You need to be thinking about harvesting minerals and resources so that you can make products. You could harvest glass, make lunar concrete, metals, etc. Need to establish communications and surface transportations, and then establish this robotic manufacturing and service capabilities. Humanity in space architecture is an ever-evolving thing. Humans and architecture have evolved together. It started out in the early development of just human shelters, caves, and then cliff dwellings and so on, or nomadic tent structures and so on. And then as humans evolved and got more sophisticated, mature, more culture, then you started seeing more development in the way of cathedrals and cities and so on. And so here we are now at the space architecture, a convergence of human and architecture as we move forward to development of other planets. And so it's important to think about the psychology of the internal architecture. Humans and nature are part of our DNA. So it's very important to think about nature and the aspects of like biophilia, bringing nature with us on this journey, bio-inspired technologies, and supporting the 9 human needs. Thinking about the psychological support features because of long-term isolation and confinement. So it's very, that's a very important part of this, and is going to continue and enable us to develop in multi-planet species. But space architecture is different than conventional traditional house design. You're designing a pressure vessel. And you've already been exposed to it. You've seen some like space station modules or type modules or inflatables, and those are pressure vessels. And you're asking humans to live inside a pressure vessel, which we're not used to doing. Yes, we can adapt to it, and yes, we can survive it. But to thrive, we've really got to think about that internal architecture. It's different than a house habitat or a house here on Earth, because here on Earth, you can just go outside and be in nature. In space, you cannot. The space will kill you. The environment is so hostile. So it's very important to think about that external environment, the radiation, the thermal, the micrometeoroids, orbital debris, and lunar dust. To think about it, long-term isolation confinement. That's so much different than your house or home that you go home to. And then there's many human stressors that living inside of a can that can cause vibration, acoustics, smells, thermal, fire, smoke, toxicity, mold, and losing pressure, a pressure breach. So the psychology of the internal architecture is really key to the success and thriving. And usually minimal functionality in systems, redundancy, reliability, serviceability, and maintainability are key aspects or features of space architecture or habitat design. So now I want to give you some background on space architecture design and considerations. I'm going to throw a lot of information at you quite quickly. The slides will be available for you to go back and look at, but I want to at least introduce you to some of the design considerations so you have an idea of what it takes to design a habitat or space architecture. First of all, you want to think about your destination, that environment. So if you're designing a house here on Earth, you're designing it for Colorado, or if you're designing it for Florida, 2 different environments, and you need to think about that environment, that destination. You want to establish that sustained human presence and Earth independence. So if you're looking at various destinations, please keep in mind those environments and how far you are from Earth. which is very important because of the aspects of sustainability that we talked about, recycling, and then the aspect of your food, water, and air. Typically, when you're doing exploration missions, there's 5 operations to consider. And so when I'm designing habitats or space architectures, lunar bases or developments, I try to think about what the occupants are doing, what the humans or the crew are doing. So that's important because that drives out an understanding of the functions and capabilities that are needed to support and enable the operations. So you think about it from the internal crew operations, the sustained crew on exploration missions, what's that take to keep the crew alive? Obviously, we talked on a few already, physiology and psychology well-being. And then you have the crew operations external of the habitat, or EVA, which I'm sure Greg or some others have talked to you already about. You have the actual mission operations, which are the objectives of the mission, and then science operations. Whatever and wherever we go exploring, we're going to be learning and doing science. And it will either be doing science on ourselves, or we'll be doing science on the geology or biology or space biology, whatever the case may be. So there are science objectives that you need to think about, as well as the very important logistics maintenance operations, both IVA and EVA. This is extremely important, and we learned many lessons on ISS about the need for all the consumables and spares and supplies, and how to bring the logistics along with you, or in some cases, from a sustainability perspective, take into account how to live off the land. Here are some space environmental considerations. So you want to consider vacuum, the debris, gravity, radiation, and dust are some of the key ones. There are more, obviously. And then you have it from the perspective of what location. So Earth orbit, lunar or Mars interplanetary transfer, and then lunar or Mars surface. And I'm not going to go into all the details here, but those are some of the considerations. Obviously, gravity, whether you're in microgravity or zero gravity or partial gravity, makes a big deal on the architecture. So partial gravity is more Earth-like, like the moon or Mars gravity. You do actually have a partial gravity. Microgravity, you're floating around. The architecture is a little bit different. There are many mission design drivers. Like I was talking about just a minute ago, the mission or science objectives related to what capabilities are needed for science, habitation, labs, infrastructure, power, launch and landing. You have your destination, like I was talking about before, which affects your environment, your flight trajectory and paths, and certainly the number of crew. How many crew you have really dictates how big of habitat you need, how much volume you might need. The mission duration also drives out the pressurized volume, redundancies and spares. How long you're there really drives out, well, do we bring all the spares with us, or do we figure out a way to make them, or do we cannibalize and repurpose other stuff? You have to think about the launch vehicles, logistics, infrastructure, and transfer vehicles. Understanding what your mission risks are, where you could have problems, how do you mitigate those, what controls you might put in place, and then the evolution of the surface space, designing or planning for growth and expansion, and then the mission costs, of course. Are you going to use technology that is off the shelf, or are you trying to use more advanced technology? And then the life support, including disposal, your whole design, develop, test, and evaluate. So from a surface outpost and base considerations, you want to think about, again, the objectives. So this is the process that I use when I'm designing a surface base or outpost, is think about the objectives, both mission, surface, and science, the location, the environment, the topology, use of any resources and any mining operations that might need to go on. And then I start thinking about the master planning, stages of development. Think about the ascent and descent trajectories so I can locate the launch and landing pads. You want to get them far enough away so that if there's an accident, it's not going to impact your habitat, or you're not going to impact it with debris or blast ejecta. And then also, how do you unload large payloads and transport them? You want to think about, so I think about the site infrastructure, utilities, establishing communications, power, and then the habitation systems, how that all integrates together. This was some of the master planning and layout that I came up with, which came up with basically 5 zones. You've got the science zone, which you want to keep pristine. That's where the science want to do all their objectives. You've got basically a power zone if it is nuclear, so you want to get that separated away. The habitation zone tends to be center to it all. You have an industrial zone, and that's where they're mining operations, so that you want as far away from the science unless you discover something, in which case the science is going to move in then. And then, of course, the launch and landing zone. So you want to have that far enough away from the habitation zone. And then between each zone, there's a lot of power, transportation, and communications that needs to occur between them all. And you have different types of layouts. You could do linear, you could do concentric, or orthogonal. And there's many examples in history of different layouts. So when you're dealing with integration of humans and surface exploration, there's many elements to consider. You have the humans as a system, the humans themselves. You have the landers, you have operations, the launch and landing. You have the habitat facility, a laboratory facility, and sometimes those could be combined depending on what your objectives are. You've got some sort of surface exploration vehicle or rover. You've got EVA, so you're going to need some sort of airlocks to get in and out of your facilities. Then you have the surface infrastructure utilities. You've got to be able to relay and transfer power and communications and so on around the base. You need to integrate all the mining operations, power, and thermal. So the interior of a habitat, everything that's inside there that is powered is creating heat. So you need to get rid of that heat. You're in a big pressurized thermos bottle, and you need to be able to get away of air to cool the air, pull the heat out of the air, but also maybe pull the heat out directly out of the computer systems through cold plates, and then move that heat, transfer it outside and dissipate it. So that's where you have radiators outside to reject the heat. So there are a lot of things to consider, including the robotics, logistics, and maintenance when you're doing the integration across all the systems. Here's an example of some of the stuff we did during the lunar architecture team studies we did. And you can see all the different aspects of this. Now, this one doesn't have radiation sheltering. What it has is storm shelters, because they were doing shorter duration habitation on the lunar surface. Because as you can see, there are many elements, many components of a surface base. And I was talking earlier, we were talking about getting inside and outside of the habitat. You have to go through an airlock to because you don't want to necessarily just open up the door of the habitat and depressurize it all. And the thing about the lunar dust, and we don't know as much about the Mars dust, but the lunar dust is very abrasive, very bad for getting to the interior of the habitat and for humans to breathe. So this was a planetary airlock design I worked on back in 1991, where we looked at a dual chamber where you had the suits in the equipment lock, and then we had the crew lock, and then we had a dust off porch where you tried to get a lot of the lunar dust off. You had maybe some peel off coveralls over the EVA suits, or you had a way inside the crew lock to remove the dust as much as you could. But the objective was to remove the dust before you come in the habitat, and also to have that transition space. Like many buildings have a vestibule you walk into prior to going into the building. These are the basic design steps of a habitat. First, assess and determine the design application, the destination, as I talked about earlier. Assess your environmental constraints, vacuum, debris, radiation, and so on. Assess the human considerations, understand the functions. What are the humans doing there? What are their objectives? what are the considerations of physiological and psychological well-being. Then you can begin designing the habitat. What are all the internal subsystems that you need for the habitat to do what it needs to do as far as environmental control and life support systems, lighting, communications, etc., as well as the external systems and interfaces to the radiators, the power system, and so on. Then I would determine some of the key design decisions. I would develop a trade tree and do trade studies on different types of whether I want an inflatable habitat or a hard module, aluminum lithium module, or some other, or build in situ. These are kind of trade studies you might do. And then we would determine the design criteria and define evaluation criteria. And so that would help us evaluate the different options and different design considerations. I kind of touched on this already, but there are many habitat environmental design drivers. Gravity is one of those. It affects the design. It affects equipment and fluid mechanisms and processes and fluid flow. The vacuum and low atmospheric pressure affects critical connections and seals and the internal operating pressure of the habitat and suits. Thermal environment, certainly that's a consideration. And on the moon, you have to consider the lunar night. Day-night cycles, circadian rhythm, have to understand that. Surface lighting, whether on the moon there's some earth shine, you need for artificial lighting for specific surface operations, but maybe at the pole you have continuous lighting or dark regions. You have to consider the dust environment. These are all things that go into designing architecture and habitats. Designing radiation protection capabilities, either the whole habitat or developing storm shelters for a solar flare to protect the humans and sensitive equipment, protecting the habitat from micrometeorite or blast ejecta, and then looking for surface resources that you could use to produce propellant or oxygen consumables or manufacture 3D components from the raw stock. And then another aspect is that surface topology and those features, how that affects your getting to the habitat, launch and landing, things of that, or possibly even using those features, craters, lava tubes, and things of that nature. So these are the habitat subsystems that are typically in a habitat: structures, mechanisms, environmental protection, life support, which is often called environmental control and life support, power management and distribution, communications and tracking, thermal control, crew and medical systems, laboratory systems, logistics, repair, EVA support, and robotics. So there's a lot of stuff that goes into a habitat, whether it's just a habitat or habitat and laboratory research capability or exploration capability. These are those items that I just listed with a short description of them. I'm not going to go through all that right now. Please take your time to go look at that later on, or you could Google on some of them and you could find out more information. Here's some design drivers or key trades that I've done in the past. So from a habitat function, that design driver is the habitat layout, whether it's a hab or a laboratory. And usually you want to separate the habitat from the laboratory functions, the quiet from the noisy, the dirty from the clean areas. The number of crew affects the volume. For long duration, I really like to get about 50 cubic meters total pressurized volume per crew member. The mission duration certainly affects the habitat size, whether you're short duration or long duration mission, because you want to have more volume, more capability inside. The structure is a design driver, whether you're using aluminum composites or inflatables. The life support, whether you're open or partially closed. A goal is trying to get full closure of the life support system, especially from a sustainability standpoint. Data handling and management, the idea of automation and autonomy in the computer systems and incorporation of artificial intelligence or AI. Communications, whether you're doing direct communications or doing relay satellites, very important aspect, design drivers, and key decision. The power generation source, like I mentioned earlier, The crew accommodations, developing and making sure that you have aspects that deal with the psychology of the crew, and then environmental protection, protecting the shelter, protecting the habitat, protecting the crew, and then understanding your risks and mitigating and putting your controls. Here are some of the design considerations on the habitat size, weight, life support system, and basically they're questions. So from a habitat, what is the required volume? You've got to assess that. How big is too big? How much is not enough? The habitat weight, you've got to fit it on a launch vehicle unless you're making it in situ. If you're making it in situ, you've got to get all the equipment there. The life support systems, do you want to become self-sufficient? What are the technology readiness? Do you have the capability now, or do you have to plan for it in the future? And so on. I'm going to skip that. Here are some quick design considerations for habitat. Short duration, you might want to use small pressurized rover or small little habitats. Long duration, you might want to look at a class 2 deployable structure or a class 3 in situ derived structure. I'll touch on that in a minute. And so on. So each one of these, you can see that they're broken into long duration versus short duration and the type of possible design considerations and how to use that. These were some rule of thumbs on habitat sizing that you could look at to give you a rough idea. As you can see, it's broken by habitat pressure, total pressure, mass, and power. And that is broken by whether it's a short, medium, or long duration mission. And so you have a habitat, laboratory broken out separately, and then the airlock is a separate element. From the past studies and all the work I've done over the years, this is about how the structures, all the habitat subsystems break out by mass fraction. So the structure or the enclosure is 20 to 25%. The eclus is a large whopping 12 to 15% of the total mass, and then it breaks down from there. Power has a high mass fraction because of it includes both external solar arrays, batteries, reactants, and tanks. So it's not all internal to the habitat. This is a kind of a cheat sheet for you on exploration of habitat functions. This is typically all the functions or activities or capabilities you need in a habitat and how they relate to each other. Dining relating to mission ops, because it could be used as a wardroom or a mission control meeting room. You've got all the different areas and different activities that interrelate to each other, and all this stuff, all these activities affect the design, because for each function you have to develop, well, what capability, what system am I going to use to satisfy or enable that function or that activity. A while ago, we developed exploration and habitat classifications. Class 1 is, think of it as a space station type module, pre-integrated, ready to go. You launch it fully outfitted and it's ready to go. You land it or deploy it on ISS and connect up the power and turn the lights on. Class 2 is a prefabricated deployable. Think of it as an inflatable habitat. You can see over here on the right some of the key characteristics of that. And then class 3, which is where we're starting to tip towards in many of the Lunar and Mars long-term sustainable developments and architectures, is in situ derived and constructed or manufactured in situ at the destination. These are some examples of the class 1 habitat, small integrated habitats, space station. Here's the space station module, lunar module here. And this was a module, actually it's a large, and not an inflatable, it's a large composite structure that's integrated with the lander and stays on the lander. This is an example of both a pre-integrated pressurized excursion module on a athlete rover system developed by JPL, and then the pressurized rovers that also go with it. And those are really considered a class 1 as well. This is a class 2, which is an inflatable habitat. It has a hard core center with an inflatable exterior. So it's packaged up and then it's delivered to its destination and inflated. This is one of the ones that I worked with a team on, and we were granted a patent. It made Popular Science years ago, as well as we won Government Invention of the Year in 2017. And these are some also some hybrid torus inflatables or expandable habitats that we designed and worked on. And then this is built in place in situ derived architectures, or we also call them automated additive construction with robotics processes and techniques to build in place of our architectures. And so our construction robotics and processes drive and inform the design to be built in place. And you want to think of simplicity, like pressure vessels, and robustness. And so in my years as a space architect at NASA, it was a lot about the internal architecture, human health and well-being. But now we're seeing this transition to, hey, we can build these architectures, these pressure vessels, these habitats on Mars, either in lavatubes or out on the surface or on the moon in lavatubes. These are some more examples of in situ derived habitats that are built in place. So I want to quickly just touch on some designs that I've done in the past. These are some of the studies that we were doing where we were looking at bringing landing modules. So we would land the first module, which was a laboratory module. And then the second one was a habitat module. And so we couldn't package everything we wanted because this was for a crew of 6 for lunar exploration. So what we did is we divided up the functions of the laboratory from the habitat so that we could separate the loud laboratory activity and noisy area and kind of warm area from the crew area, which you want to keep cooler and quieter and activities related to that. And then what we did when I was talking about repurposing or recycling is every time we brought a logistics module, we would retrofit it and turn into either a medical operations or a biolab, an exercise area, or we would have that detach and be part of what we could go on exploration, loaded up on the triathlete. So here's some parameters from that work, just describing that we used basically aluminum lithium hard shells, 3.5 meter internal diameter by about 8 meter length. Again, that was partially driven by the launch vehicle capability there. These are some of the sketches we did showing some of the internal architectures, showing some of the division between the laboratory and the habitatory, separation of those activities and functions. This was an inflatable lunar habitat I designed back in 1989. One of my first inflatables when I was at the University of Buffalo, I got interested in bird air and tensile fabric structures. Well, when I got going into NASA, that was one of my first assignments, and my first things I worked on was a tensile fabric structure. It just happened to be an inflatable for a habitat. And so that was a spherical habitat, 16 meter in diameter for 12 crew members for a 1-year stay. This is some of the internal architecture that we developed for that. And as you can see, we did radiation protection, put it around the outside of it. Then I designed, about 1992, a horizontal cylinder. Same amount of volume, same crew, 12 crew for a year-long stay on the moon. But I wanted to look at the internal architecture, difference of a sphere versus cylinder versus a torus. And what I learned is the cylinder was more amenable to the internal architecture and layout. And it was a bit easier to construct and assemble. And another unique thing I did is I put all the Eclipse hardware, all the life support systems in 2 redundant modules so I could have all the heat, noise, and toxicity kept away from the crew, and then the systems, your air return and air supply and water and so on, runs through the habitat, but all the processing is done in these modules, and you could service them there. I did in the around 2007 is the idea of a hybrid mid-expandable. So the idea of using hard end caps with an interior mid-expandable. And you can see here, this is a design concept that I came up with. And then we kicked it around a bit at NASA, and then NASA Langley actually built a prototype of it. This is a hybrid torus habitat that has the internal hard core, and then the inflatable torus is packaged around it so that it can be delivered as a smaller package and then inflated. I also worked on some built-in place in situ habitats where I looked at different ideas, both surface and in lavitubes. And the idea here was to look at automated additive construction, robotics and processes, looking at how you might use lunar concrete to develop and build these in-place habitats. And these would be large structures and permanent capabilities. So there's many lavitubes on the moon, and now we're finding out we think they're on Mars. And each of these lavitubes are unique. So you could tailor this, and here's kind of a cross section of a lavitube with the idea of putting a rover port on top of the surface with an elevator system capability tunneled down into the lavitube, and then the large, think of it as an office tower almost, with multiple levels and bulkheads, tower bulkheads, separating these in case you did have failure or a pressure breach. So there's many ideas about what could be done, and this was some of the ideas I had and some of the stuff I worked on for in situ built habitats. And here's some a cylinder, both short and tall cylinders of different diameter capabilities, and or a conical design as well. And each of these have different capabilities, different functions, and are really designed to house hundreds of people doing many activities and functions and many operations for sustained human presence and permanent capability to develop a robust ecosystem. So space architecture is really about enabling humanity to become a multi-planet species. It is moving to the forefront of design and development for many space agencies and private industry. Matter of fact, I just read that the Hilton wants to put up a space hotel based on that inflatable habitat design I showed you earlier. So to me, space architecture is a renaissance of traditional Earth-based architecture. It's an evolution of the profession, but it's providing that base, and that's why I say it's a renaissance of it. It's getting back to the basics, providing basic human needs of shelter, protection, and their physiological and psychological well-being. As I mentioned earlier, architecture has evolved alongside humanity, and we're at that tipping point in space commercialization where it's going to converge and enable humans to push out, to become a multi-planet species. Again, harping on the psychology of internal architecture, how important it is, because humans living inside a machine is not natural for us. So it's going to take a lot to really overcome that. And I also feel that space architecture is a bit of a paradigm shift, especially for Lunar and Mars, partial gravity. I think there's a lot of planetary architecture and maybe even hybrid mechanical, electrical, and plumbing systems that we could enable to be used and not just all rely on the extremely expensive space systems. And then also we need to understand what's applicable from like international building codes and standards, because right now it's a wild west out there and we need to establish these codes. Otherwise we will have some catastrophic events. So I want each of you to think about that the journey begins with an inspiration. And I dare each of you to dream, to be inspired, and to inspire others. So that is what space architecture is. And if you have the drive, the desired drive and determination, you can succeed as well. Thank you very much.
Awesome. Wow, what a presentation, and let me bring you up here. That was incredible, and I just wanna start with this question. There's just so much that you covered and the complexity of how do you use the resources, and the planet you're gonna be at? How do you design the facility? You talked about architectural design, the psychology. How does one person as a space architect, are you a team, of people that design these?
Oh, absolutely. It's a team
Incredible.
effort all the way around. And I know I harped a lot about architects and space architects, but really it's engineers, it's scientists, mathematicians, computer programmers, just the list goes on, human factors and so on. So absolutely it's a team effort. And you can't, no one, I don't think any one person could do it all by themselves, although I have tried. But it is a lot of work, as you can imagine. Think about designing a skyscraper or a building in a city. It's not just one person; it's a team of people, and not just the design team. You've got to take into account the manufacturing team, the construction team, the operations team. And so, you got to think about it from cradle to grave, the whole life cycle and all different aspects of that. And so many teams are involved. And then, from the procurement team, the contracts team, the legal team, they're all involved.
Is the space architect the visionary, the one that kinda has, like, the grand design in mind that brings together all the teams?
I would like to say yes, but no. The grand visions come from anybody and anywhere, and I really vision, and that's one of the things I teach my students is um, to have a vision of their project. What's the vision of your project? To enable humanity to become a multi-planet species. Well, what's your mission? My mission is to design habitats that can be constructed on Mars. And then what are your goals and objectives? And so from a vision perspective, that can come from many people or a combination of people collaborating together on a vision. And to be a visionary, I don't know, I wouldn't say that just architects or space architects were kind of trained in a creative way, in that way, in our traditional training, but certainly many engineers and scientists are very creative and very visionary as well.
Chris, that was one of my questions for you was after doing this for more than 3 decades, how do you stay creative?
I paint.
Oh,
um, I do a lot of well, I don't do as much as I used to. I dabble in design, so I still do some design work if it interests me or if I have the time. I do creative outlets, painting, some writing from time to time, teaching. I teach at the University of Houston, the Sasakawa International Center for Space Architecture, and so the students keep me on my toes. The graduate students in their various research projects. And so, I think um, you want to keep pushing yourself and keep learning and there's many different avenues of learning. And so just anything to keep creative juices going and keep the thought process moving.
wonderful.
Well, let me start with a question we got live while you were presenting, and it's about a matter of space. So, how do you determine a maximum or minimum space you need for your base?
So, like I was talking about, and that's why I wanted to just share the slides. I have some rough rule of thumbs, and for the most part, you go by the number of crew and the crew size. And so, over the years, on all the different designs I've done parametric sizing and analysis to determine that roughly 50 cubic meters per crew member for total volume of a habitat. And so if you have 4 crew members, maybe you want around 200 cubic meters of volume. Now that's not free volume, that's total pressurized volume. And so that gives you in the ballpark. And there's some other numbers like that that give you a rough idea. But that's what I use. So if you have, like I said, if you have 4 crew members, it's 200 cubic meters. That's roughly one space station module size. They're a little bit less than that. Actually, they're around 125, I think, cubic meters, but that would give you in the ballpark. So those rule of thumbs that I showed you earlier can put you in that ballpark. Whoops, I just dropped that out. Okay, and next question.
Yes, this one may be kind of more technical for the mission today as well. Space doesn't have enough oxygen. How can they build a space base that could supply the oxygen in there? It's from Indonesia.
Well, that's tricky, because if you're in low Earth orbit or in space, where do you get your oxygen from? You need to bring it with you, either in water form and break it into hydrogen and oxygen, or you need to bring your oxygen with you. Now, if you're on another planet and maybe the resources there that you could mine for oxygen, either in water ice or it's embedded in the soil somehow, and then you can break it out. And in Mars, you can actually, with a Sabatier processor, you could take the carbon dioxide out of the oxygen, mix it with a little bit of methane, or not methane, but hydrogen, and then break it into different components and get oxygen that way. So depending on your destination, hopefully you can find oxygen. Otherwise, you're going to have to bring it with you.
Did you want to show us anything on the slides?
Oh, this was some of the information I was talking about earlier about total pressurized crew volume. And so whether you're short duration, medium duration, or long duration, kind of the ranges that you're working with, that just gets you in the ballpark. You really need to do the design work. But, if you're trying to start out and you just don't know where to start, that'll kind of get you in the ballpark about volumetrically how much volume you need. And then you can begin to size your cylinder appropriately from that.
Got it. Okay, a question here related to life support. And I know these haven't actually, been built on Mars yet. So we can do this as a prediction of what was the largest challenge you faced in troubleshooting a life support system in space. So what would you think would be some issue that comes up?
Well, for life support, it's a complicated system, and the systems for ISS and zero gravity are even more complicated because you're in a microgravity, and fluid does not flow properly. So you have trouble with that. So you have a lot of pumps and valves and backflow valves and so on. And life support systems are critical systems, Crit 1. So you need to have dissimilar redundancy and backup. And it's very heavy, and they're very power needy. And they give off a lot of heat. So they're critical to our existence, but they're our biggest nemesis in the habitats. They weigh the most, they need the most amount of power, they give off a lot of heat, and they seem like they're always breaking and need repair. So there's a lot that needs to be done in life support systems to get them where they are sustainable. And certainly, I think, our goal is to get closure of the life support system. So we're recycling all our water, all our air, and making use of all that with minimal makeup. And those are some of the goals of life support. But yeah, they are a big driver. The life support is a big driver, and bioregenerative life support, which is now introducing the idea of growing food, and the food is producing oxygen, it's using CO2. Now it's beginning to close some of the loop. But again, that requires a large amount of volume to grow that food. Even if you do get creative on how you could package it, you still require that all that operations, all that activity, and life support's a big challenge. It is.
And I guess that's part of why we have the International Space Station and testing these systems out to see, they're closer to home, but once we send astronauts to Mars, it's a whole other challenge.
So I want to just touch on that just real quick. The space station primarily and initially was all about the research as a laboratory in space. And it really wasn't a lot of thought given to the internal architecture. It was to a certain degree, and I've talked to many of the people who worked on the designs and all of that. But from an internal architecture psychology aspect, yeah, it's not that desirable to live there. So it was really about working there and learning what we need to know to enable us to go to Mars. And that's its primary function, its primary capability is that. And now we're adding in and learning more about, hey, we need to think more about psychology. We need to think about, the crew members, long-term isolation, confinement issues, these kinds of things that we have to solve and bring a little bit of that nature with us to make it more amenable, so that we as humans can thrive.
I have a little bit of a more personal question. And I said you love to paint and do some other creative things. What else do you like to do for fun in your free time?
Actually, I love nature, and I love to go out in the woods and do hikes and walking. I live on a lake, so I do a lot of boating and get out in the water and so on. So I'm really connected to nature, and that is one of my biggest things. Obviously, got the fall beard going, but I do. So from a creativity perspective, I pay attention and I watch nature. I watch, the simplest things like ants, how they build a colony, how they work together. I watch birds, and I watch, animals just scurry about doing their daily thing, and what they're doing and how might that apply. So bio-inspired engineering is amazing to me. If you've ever looked at Boston Robotics as an example, a lot of the robotic systems are inspired by animals and nature. And so for me, I get a lot of inspiration or creativity from that.
I'm going to ask one last question. This is from the pre-submitted on your motivation in becoming a space architect. How did you get to this place here?
Well, that's a really interesting one. It'd take another hour, but I'll shorten it up for you. So to make, let's see, where do I start? So I grew up fairly poor in rural New York, up by Canada. And to make a long story short, I ended up, working my way towards becoming an architect and working for architectural companies. By chance, and it's weird, I didn't grow up a Trekkie. I didn't grow up, a space nerd or whatever. You think I would have, right? But I didn't. It was more about opportunity and seizing the day. And that, if anything, you get anything out of this presentation, is for everyone to look at each day and seize that opportunity to do the best you can. And so I had an opportunity. I was looking to go back to graduate school. I had moved from Buffalo to Houston. I was looking at a couple of schools. I found out about this program. I talked to Guy Trotty and Larry Bell. It was about space architecture, and I was hooked. I was like, oh man, that is the next thing. I'm thrilled. So I spent 2 years doing my master's there, and then I got the internship at NASA, and they hired me. So that's how I ended up there. But it was more about, I was so inspired about the idea of space architecture. Think about it, the next evolution in architecture off planet. And so it's just, all those sci-fi movies, I love them because I'm always looking at the architectures and looking at the designs and the creativity there. And some of it's, not believable, but still it's inspiring.
So whenever I work with my students, we talk about like lunar or Martian habitats, they'll go to Google and search it. And a lot of the images you presented are like out there. And I now have met you, which is so cool that you're like behind those.
Yeah, the students can go to my website and look at a lot of my architecture, both terrestrial. Most of the terrestrial stuff is residential, but certainly all the projects I worked on at NASA over the years are there. And it's technaarchitects.com. That's I think it's in my beginning slides, TECHNE dash architects.com. Anyways, there's a lot of those images. Yes, a lot of those designs, and I did lead many of those design teams, and I was inspirational in a lot of the designs that were developed. But like I said, it was a team effort. I didn't do it by myself. And yes, a lot of those designs are from work that I have done or participated in the past.
So my final question now, as we're ending, we have students from around the world watching, middle school, high school. Any words of advice or encouragement for those kids?
Yeah, stay true to your dream. Work hard, have the desire, drive, and determination, as I had put on my slide. Um, you know, and take every opportunity to seize it, like seize the day, as I said earlier. Take every opportunity to go learn about something. You never stop learning, so just keep pushing forward and be persistent and confident. Have confidence in your ability to succeed, to learn, to do whatever you want to do.
I love that. And seize the day because we have one more day of space teams, which is tomorrow. So I want to wish the students the best of luck as you wrap up day 5 in designing that habitat. Hopefully, you got some great advice. I have uploaded your slides, Chris, to the learning platform, so they'll be able to access those. So for now, we say goodbye and we'll see you guys tomorrow. Thank you again.
Thank you very much. Bye.